So that too.
Thank you very much. My name is Judith Tács, and I'll be presenting my work on evaluating contextualized language models for Hungarian. This is a collaboration with Dániel Lévai, Dávid Nemeskei, and András Kornai. And David gave a really good introduction about contextualized language models. So basically, these are language models that work at the sentence level instead of the word level. So we are used to GloVe and Word2Vec, which assign the same vector to every occurrence of a word. On the other hand, contextualized models take into account the sentence or even a larger context of a word. And they can assign different vectors to the same word. For example, the word running in these two sentences would be represented by a different vector. The most famous contextualized language model is undoubtedly BERT at this point, with over 15,000 citations in less than 3 years. BERT is a transformer-based language model with over 100 million parameters, depending on the version, which David mentioned. The Hungarian version, which is the BERT-based model, has 110 million parameters. And it improved the state-of-the-art on many tasks, including previously very difficult high-level tasks in the collection of GLUE, SQuAD, and question answering and SWAG. And originally, the BERT authors released 6 pre-trained checkpoints, 4 English and 2 multilingual, which I'll be calling MBERT. Later on, this was expanded by many BERT variants, and which are different in architecture or the training objective or the training data. And Hugging Face, a New York-based company, released a library named Transformers, which includes PyTorch models for all of these models, or most of these models. They have over 30 model classes. They have a repository for pre-trained checkpoints, so this is a community repository. Hubert is available in this repository along with over 1,000 other models, and very recently they added a dataset repository as well. There are a few models that support Hungarian, and these are the 5 ones that we worked with. Well, the first one is Hubert, which doesn't need an introduction after the previous presentation. The next one is the multilingual BERT, which supports 100 languages. It was trained on Wikipedia, and it's the same model as Hubert and BERT base, so it's 12 transformer layers and 110 million parameters. The next one is XLM Roberta, also a 100 language model. It was trained on Common Crawl and has the same architecture but had a different training objective. And there is a larger version of this model called XLM MLM 100, which has 16 layers instead of 12 layers. And the 5th model that we worked with was a distilled version of the multilingual BERT. This means that they train a smaller student model that tries to imitate the teacher model, MBERT. And by this, they create a much smaller version of the model in the hope that the performance doesn't suffer too much. And these all support Hungarian, of course. Now, the method we used is called probing, which is a popular evaluation method for these large black box models. We call them black box models because the functions that these models implement are so complicated that they are impossible to interpret. So we don't really know why the answer is A or B. And their evaluation and interpretation is limited and mostly in English, especially for high-level downstream tasks. And probing is a popular method where the basic idea is that we want to learn whether a model encodes certain information. And the way we learn it is that we try to recover this information from the representation. And if we can recover it, then we say that it contains the information. The typical steps look like this. So we take a language model, We freeze the model. This means that we do not fine-tune it on the data. We extract the representation of a word or sentence or paragraph. And on this representation, we train a small classifier. It's important that this is much smaller than the model itself, because we are more interested in what the model knows, what the model contains, than what we can train on top of it. And if the classifier performs well, then the model contains the information. We can conclude that. There is criticism of this line of work, but since we are just looking at trends, it will help us a lot. This is our probing architecture. So the steps are the following from bottom to top. First, we perform subword tokenization. So all these models have subword tokenizers, which work with fixed vocabularies. So we have a fixed set of subwords, and every input text will be mapped into a sequence of these symbols. And it uses an unknown symbol if necessary, but it almost never happens. Certainly not for Hungarian. And so we tokenize a sentence. We feed it to the language model. This is the second box. I hope you can see my pointer. And we pick a layer of the output. So if we have 12 or 13 layers, we either pick one or sum them or use a weighted sum. We pick a subword, which I denoted with red here. So we are taking the subword that corresponds to this token. We take the last one in this example. We train a small multi-layer perceptron on top here. So this is just a small neural network with one hidden layer and ReLU activation. And we compute loss against some linguistic label. Okay, what are these linguistic labels? So what are the tasks that we had on our hands? The first one is morphological probing. So in this case, we define a task as a pair of a morphological tag and a part of speech tag. So, for example, here's an example. What is the tense of cut in this sentence? So, if we have a morph tag named tense, and we want to end a part of speech verb, then tense verb would have samples that look like this. I have a sentence, I have a target word, which is red here, and I want to know if the representation, if the language model knows that this is indeed the past tense. For POS tagging, we do the same, but we repeat the classification layer for each tag, so for each word in the sentence. And the same for NER tagging. What is our data? So the data is most interesting for morphological probing because we had to generate it. We generated this from Web Corpus 2. For each task, we generate 2,000 train and 200 Devon test sets. Each sample looks like this. So we have a sentence, a target word, which was read in the previous example, and a label. So it could be past tense or present, or any or other labels in other tasks. And we take care that the target words do not overlap between splits. So if something is a target word in a train, it cannot be in the dev or the test set. And we oversample rare tags to make the classes more balanced. And with this sampling method, we could create 11 tasks for Hungarian. So this is what we could generate from the morphological tagging of Web Corpus. So we use the UD morphological tagging schema. And here you can see that we have the highest number is 18 values, so we have 18-way classification for noun case in Hungarian, and the rest are 2, 3, or 4-way classifications. Okay. For POS and NER, for POS we use two kinds of data set. We use the Szeged Universal Dependencies corpus, but since it's pretty small, we decided to include a larger data set. So we sampled 10,000 sentences from Web Corpus. And for NER, we use the Szeged NER corpus. And before I turn to the results, I want to briefly talk about the segmentation. So I mentioned that all these models use subword segmentation. with a fixed vocabulary. And multilingual models have a shared vocabulary for all languages. This means that they use the same subword vocabulary for 100 languages. And we examined how good these vocabularies are. So here are some of the statistics. The full tables are available in the paper. So the vocabulary size for Hubert is 30,000, but it's Hungarian only, and the rest have much larger vocabularies. The second row is the average length of a word in word pieces. So this means that how many parts a word is split into by the tokenizer. And we can see that Hubert does the fewest splits at 2.8, and the rest of the models split Hungarian words into more parts, which is not necessarily a problem, but we will see that that Hubert actually works better for Hungarian. And we compared it against EMTSV's segmentation, and of course exact matching is very rare, so we only had it in 16% of the case, and surprisingly XLM Roberta is pretty close. And we also computed the proportion of word types where the last word piece is the same, because Hungarian morphology tends to concentrate at the end of the word. So we have it's the same. Hubert has almost the highest one. Actually, XLM Roberta has a higher 47% identity here. Now another plot about the segmentation. This shows the lengths in subwords on the x-axis and the log frequency lengths on the y-axis. And what we can observe here, is that Hubert not only generates fewer subwords, but it also tends to undersplit the frequent verbs. So frequent Hungarian words are less frequently split by Hubert than the other models. This is not surprising, given that Hubert's vocabulary was trained on Hungarian text. And now on to the results. So for morphology, what we see is that using the last subword instead of the first one, because we tried both, is almost always better. There is one exception, the degree of adjectives, which is not surprising since the superlative is a circumfix in Hungarian. Hubert is better than all the other models, particularly in the lower layers. And Hubert is also better when we use a weighted sum of all the layers. And here's a plot of all the accuracy of the weighted sum of all layers, and we can see the blue one is Hubert, that it's always better, and but the difference is not always as large as with others, and generally these tasks are not too difficult, so we rarely see performance under 90%. And we can also see that Distill Ambert is not so good as the others, and the second one after Hubert is probably XLM Roberta. And here's a plot of the layer-wise behavior, which I have to rush over, but we can see that Hubert's advantage, again the blue line, is more pronounced in the lower layers. For POS, what we see in these plots is that we compare the first and the last word piece, because it's not obvious which one to pick, and we see that the last one is generally better for all models. And again, Hubert is the clear winner. In both cases, Distill Ambert is the clear loser. And we also looked at the layer-wise behavior. So we split it into 4 layers. There is an embedding layer. This is the first one, which is just a basically just a matrix projection of the word pieces. So there is no contextual information here. This is the first contextual layer. This is the last one, and this is the middle layer. So this is located in a different place in the different models because they have different numbers of layers. And we can see that that Hubert is really good at the embedding layer and the first layer, and the difference shrinks as we go higher in the layers. So this is for POS tagging. And we see a similar picture for NER. So here we see that the embedding layer is really bad for NER. And as we go higher in the layers, the first layer is pretty good, but then the difference shrinks, and we see kind of a plateau in the middle layers, and actually the last layers are not as good. And in conclusion, we compared Hubert against 4 multilingual models. Hubert was better than all models, particularly in the lower layers. And Hubert's segmentation is closer to a morphological segmentation. And the last subword is almost always better. And we released the coded data and the 4 result tables here. This will be uploaded next week sometimes. Thank you for your attention.